All of you, myself, Rita Sharma, Associate Fellow, Terry, welcome you all in this afternoon session on linked open data in digital library. Linked data is gradually becoming instrumental in opening up resources in digital libraries, not only to human, but also machines. Machine processable and linked description of resources have made way to new service models and technologies. This session hosts 3 keynotes involving 2 linked data platforms, namely DBpedia and Wikidata, and another emphasizing their relationship with digital library service design. To chair this session, I would like to invite Dr. A.R.D. Prasad on the dais and take the proceeding of the session forward. Dr. A.R.D. Prasad is former professor and head of the Documentation Research and Training Center, DRTC, Indian Statistical Institute, Bangalore. He obtained PhD in Artificial Intelligence and LIS, Karnataka University, and Associateship in Documentation and Information Science from Indian Statistical Institute. He was a Fulbright Fellow and is member DSpace Governance Advisory Board, MIT, USA, member Project Evaluation Committee on E-Infrastructure, European Commission, Brussels, High-Level Committee member, National Mission for Libraries, Government of India, member, University Grant Commission of India, Curriculum Development Committee, and member, Electronic Thesis and Dissertation Committee in FlipNet, consultant, UN FAO, Rome, and consultant, UNESCO, Paris. His areas of work include semantic web, digital libraries, and open data and data repositories. So with this, I request Dr. A.R.D. Prasad to please take further the proceeding of this session.
Yeah, thank you for a generous introduction. First, let me thank Professor Parthapratim Das for giving me the honor of chairing this particular session. Okay, let alone the participation, inviting me to participate in this esteemed conference. And definitely, I am quite pleased to chair the session on on open data, especially linked open data, semantic web related stuff. So I guess I'll have much to learn from the speakers, though I also just put my fingers in some of these areas from a different perspective perhaps. For me, for example, the linked open data is much related to library classification, using that as a tool to link the data sets. In fact, we came out with a fancy name called Promise. That is, we have metadata for various functions. We have structural metadata, administrative metadata, preservation metadata. We are tying with the idea of metadata for processing the data, so that when we process the data through various robots, it could be expectation-driven processing, and whether we can extract the data from cell level. Okay, that is what is that we are experimenting. I am sure from the 3 speakers we have, we all have a lot to learn. So first I would like to invite Dr. Sebastian Hellmann, and he is a senior member of the Agile Knowledge Engineering and Semantic Web, also known as AKSW, research center focusing on semantic technology, often in combination with other areas such as machine learning, database, and natural language processing. Dr. Hellmann has completed his PhD at the University of Leipzig. Hope I by-hearted the pronunciation of your university correctly. Okay. In 2014, on the transformation of NLP tool output to RDF. He is the head of the Knowledge Integration and Language Technologies Competence Center at InfAI. He also is the executive director and board member of the non-profit DBpedia Association. Dr. Sebastian is a contributor to various open source projects and communities such as, NLP to RDF, DL Learner, OWLG, And Dr. Hellmann is the author of over 80 peer-reviewed scientific publications. And he was chair at different symposia like Open Knowledge Conference in 2011, the workshop on linked data in linguistics, the Linked Data Cup 2012, multilingual linked data for enterprises in 2012 workshop, the NLP and DBpedia workshop in 2014, and many others. Now I look forward to listening to Dr. Hellmann along with you guys.
Okay, yes, welcome everybody, and thank you for giving me the opportunity to speak here. And I will give a brief, or actually a quite extensive talk about the DBpedia history and the challenges. So there are 4 phases basically. So DBpedia is a very long-term project. It's now 12 years old. And I'll talk about the beginning phase, which is the first 4 years. Then there was a manifestation phase where everything was better structured. This was 5 years. And then I'm talking about something special, a glass ceiling phase. So this is a phase where we had a lot of problems and a lot of challenges, and we had to discuss how we handle them. And then I'll present some lessons learned. And then the last part is called the future or bring solution. I called it the skyrocketing phase because as a community we have we have the feeling that we have solved many of the problems that we encountered in this glass ceiling phase. So let's talk about the beginning. So the DBpedia was a project that extracted facts from Wikipedia's info boxes. So you can see here, this is it's a screenshot of the National Digital Library of India article from the English Wikipedia. So if you go there, you can see it on the right side. And then if you click on this link, you see the facts that we extracted as triples. So this is straightforward, also displayed here. And now I'm going to show you something which is quite recent, and it's also a Wikimedia funded project. So we have new global IDs which you can access with the Wikipedia identifier, or there's also a hash for this ID. And if you click on it, you get an overview over the data we extracted from all the languages in Wikipedia. So here you can see a direct comparison of these sources, and there's also, for example, very small wikis like the Telugu language. So now here, it goes towards the debugging interface where you can directly compare different values. So if you look at it here, then maybe somebody of you speaks Telugu. So I don't know, maybe it's the same, but actually they are written differently on Telugu, Wikipedia, and Wikidata. Yeah. So go ahead and fix it if it's wrong, or maybe it is good or valid. But there's a lot of information extracted. So for example, you can see the number of employees. So National Digital Library has 100 employees. This is from the English Wikipedia taken. And then you can also query for the city. So this is a direct access to the database. And then you see that Wikidata, for example, has the city where the National Digital Library is on. So this is a new interface in collaboration with Wikimedia as well to compare data between data sources and sync them. So what was the first achievement there? You could, in 2007, so 12 years ago, you could query Wikipedia like a database. So the famous query is soccer players who are born in a country with more than 10 million inhabitants who played as goalkeeper for a club that has a stadium with more than 30,000 seats. And the club country is different from the birth country. And then you could write a Sparkle query and it would give you a lot of results. So this is the actual live query I was performing now on the online database. So this query has been working since 12 years and it has steadily improved with the extraction. and it's online, no password, no registration required, you can just query it. So these were the starting members back then in 2007. What also was one achievement, there was an exceptional boost of research and industrial innovation around DBpedia. So DBpedia, the data set, became the foundation for around 25,000 scientific papers as of today. There was high industrial adoption, so BBC included DBpedia, New York Times linked to us, Yahoo copied the extraction software, and Watson also solved the Jeopardy challenge with DBpedia as one of the data sets they used for it. And it helped the emergence of semantic technologies because it served as an excellent test bed to develop your tools, because there was really a lot of data where you could try your tools. So these areas are knowledge extraction, entity linking in terms of databases, then entity linking from text, this is natural language processing, and also graph database research. Another achievement of this initial phase was that the linked open data cloud crystallized around DBpedia because there were stable identifiers that you could link to, and so everybody did. And you see that we bootstrapped this over the years, and it grew, and DBpedia became more the linking center during the years, right? So the main reason why we need decentralization is that it scales very well. So you cannot have a centralized approach and expect from it that it scales. But this is a decentralized network of data, and this can scale arbitrarily like the World Wide Web. And the links connected. I posted here the design principles from Tim Berners-Lee. I think you know the 4 rules. I would just mention the 4th rule because I'm going to use it later. So if you publish data as HTTP URIs on the web, you should include links to other URIs so that they can discover more things. So this is called the identifier linking paradigm. And I'm going to talk about it a bit more later, just so you know the origin of it. So then there was a manifestation phase from 2011 to 2016. It was a very big growth phase. There was internationalization, so we didn't only extract the English Wikipedia, but all 140 languages, and then language chapters formed, and we had a mappings wiki where you can edit the ontology and data cleaning rules, and we included Wikimedia Commons, we included Wikidata, we included natural language processing data set. And then there were a lot of community contributions and ontologies which were contributed. So that's why DBpedia has now 8 different taxonomies which you can use to query the data. And then we reached 14 billion statements. And also during this manifestation phase, we founded the DBpedia Association in 2014 as a non-profit. And now we have a reliable core of organizational supporters, and they guarantee the sustainability and the network multiplication. So it's a network about a non-profit coordinator in Leipzig, DBpedia Association. We have our own research topics in Leipzig, so we are more primus inter pares. So all the people you see here, the organizations, they are excellent in research and excellent engineers and technology leaders in their area as well. Now I'm talking about something which was a bit problematic. So we had something I called it glass ceiling phase as a metaphor. So glass ceiling is normally a term from gender inequality. You see a woman on the right side trying to climb the career ladder, but then there is some invisible barrier that keeps her from pushing upward in her career. So in general, women have to work harder than men for their careers. And so the thing here is that you have some things like an invisible glass ceiling, and you push harder, but you yield less and less result, and you don't come forward in a sense. And this glass ceiling metaphor totally applies to all data projects. And I'll tell you later that there are no exceptions to this. So we had this feeling to come to a glass ceiling. We didn't have any good growth anymore, healthy growth, organic growth, let's say. So what happened during this glass ceiling phase in the world? So actually now there's a fierce competition over the editorial workforce. So there are many approaches that want you to go there and edit your data into their portals. So there's ORCID, Wikidata as well, although Wikidata is a very good project. Microsoft Academic, Google has now the feedback button, and 1,000 more want you to add your data to them. And then there's something like the identifier wars. So this is caused by actually maybe it was also caused by us because our identifiers were very popular, but there's the identifier wars. So everybody wants you to include their IDs in order to gain attention and workforce and backlinks and everything. What also happened during the last 3-4 years is that there are a plethora of data graveyards. So project ends, it runs out of funding, the data set goes down, is dead, hosting is gone. So what did we do? We were mostly inactive, but we formed a think tank with our members and community, and we discussed and redesigned to what to do with the class ceiling problem. Result was, with the problems in general, so the result was that open data needs a scalable business model. So if you want to have better data, you need to have a scalable model. And we identified many problems of decentralization and then innovated to provide a solution to boost decentralized approaches. So we think that only this coordinated decentralization is able to break the glass ceiling. The foundations are taken from a book, from a project which resulted in a book. It was about aligning software and data engineering, and this book defines 3 dimensions to evaluate data-driven systems. So if you want to evaluate your system, you have to look for productivity, quality, and agility. So agility is how easy it can change, schema-wise, data-wise. Quality is the overall quality, and then productivity is how well when you work, how productive it is. And these 3 are closer described in the book. And now I come to a section explaining this glass ceiling, and I call it the 4 riders of the data calypso. And the first one, the law of diminishing returns, is actually the one that causes a lot of problems down the road. It's intrinsic to data quality. Second one is copying data, which is a duplication of effort. There's non-collaboration by data publishers, which is also multiplication of effort by individual non-sync data sets. And there's a network disaster of linking and mapping, so it's another type of multiplication. So the law of diminishing returns comes from economic, and it just means that if you increase one factor of production, in this case in data mostly the workforce, then you come into an area that goes into diminishing returns, which means you get less and less per editor time. And the law totally, so the data quality is always Pareto efficient. There's a 20-80 rule. You're most productive when your database is small and in the beginning, and then if you invest more effort, it gets harder. More data coverage means lower quality, because you have more data. And more quality means also remaining errors are hard to fix. And then update is also more difficult to create. So if you have 100 million records and 10 million of them needs to be updated from different sources, it will get really hard. So these are the problem. And then here's another aspect which also accounts for us. I mean, we also had a large online community maintaining the ontology. So online communities are generally great. They are easy to motivate, by the greater good, or you get better data. And they also work for free. So it's a 0 or low cost on your budget. But if you are already in this diminishing return phase, what actually happens if you manage to double your community activity? You don't get twice as much data. You get maybe 25% more. And you don't get better overall quality. Do you get better overall quality? This is also not guaranteed if you increase the size of the data. So it's not just that you can throw more people at the problem and it will just go away. No, there's diminishing returns. During this glass ceiling phase, we also researched extensively test-driven data engineering. It sounded so great back then. You write tests, the tests run over your data, they tell you exactly what's wrong, you fix it, you are done. The former CTO, Dimitris Kontokostas, wrote a nice, very good paper together in a joint project with Dutch libraries. Enno Meijers is here. Then he created edited a W3C standard about testing shapes constraint languages. But then in the recent years we discovered also test-driven data engineering follows the 2080 rule. So it's also Pareto efficient. So you write a small set of initial test cases and it's very efficient. And then if you start to write more and more tests, it will get less and less efficient. And in the end, if you make the tests too small, you have to have one test perfect in your database, and it is like editing the fact itself. So it increases a bit of the efficiency, but it doesn't beat the law of diminishing returns. We also had to learn that. So there are no exceptions to this. Rider number 2 is copying data. So let's say you have 10,000, you publish your dataset on the web, like us, 10,000 downloads of a dataset dump. So let's say you have one unparsable line in this dataset and it needs 15 minutes to find and fix. Then you have 104 days of work downstream from the people who downloaded it. Then the publishers here are really very much struggling with data quality because of the law of diminishing returns. But actually their consumers have invested 50 to 5,000 more times in cleaning the data they downloaded there. Because that's the first thing you do. You download the data, and the second step is you clean the data. That's the normal data science approach. Yeah? And if you could just capture some of this consumer invested time, I think we wouldn't have so much problems with data quality because we just had a larger, more amount of people helping. Especially the consumers, because they have, the consumer is very special. Data quality is fitness for use. And the data provider doesn't know this really. The consumer knows data quality because he uses the data. Yeah, so they have a different view on the data altogether. So that's the valuable part. Rider number 3 is the non-collaboration. So you see all these organizations here I listed. So the commonalities between these organizations is they publish open data. This open data is license compatible, and they also have an overlapping space. So they go about authors, creative works, papers. So actually you could merge and sync all these data, but instead each of them fights their own fight against the law of diminishing returns. So they have to invest the work to improve their data set. Wikipedia and Wikidata are a bit special because they copy it from outside sources, so they kind of like increase it again because they open a new data issue problem in the end. But it's good to have it collected, I have to say. So that's something. And there's no syncing algorithm now. I'll introduce that later. Because syncing and upstream would actually solve this a lot. So if we could coordinate all these databases and all the lot cloud and all external databases in their editorial processes, this would solve it in the end. And we are trying to do this with the Global Fact Sync, which is a MediaWiki funded project here. There's also rider number 4, network disaster of linking and mapping. And it is about the complexity you need to link different data sets, decentralized data sets. So if you do each with each, you have a complexity of n squared divided by 2, which is 20,000 mappings for 200 data sets. If you follow this identifier linking paradigm, you have actually O of n, which is much smaller. But then the problem is that this is on the publisher side, and the client side also creates links, and they also have to implement work for crawling. So this is also the thing that consumers invest much more time into the data than the actual publisher, again, when they download it. Yeah? That's something which is very, very important. So here we propose a knowledge library later. Okay. So now I'm coming. This finishes the first part, like the historical part. Now I'm coming to the future and what already has been implemented and things that look very promising in solving many of these things. So we also followed a platform approach. Platform also always means that you have some sort of less work and more benefits. And we also, I mean, we already identified that open data is in the sense too altruistic. Yeah, you do open data for others. That's the main reason why people do it. But we think that there should be clear incentives for publishing open data. And one of these incentives is that you get effective third-party contributions. This is the upstream and thinking I'm talking about. And this is really valuable because it frees you from all the difficult data quality work you have to do, each one has to do on site. Then there should be an open data business model. Open source software is a very successful business model. Yeah? Why not open data? Why is there no open data business model? We are not there yet, but we are discussing many things, how open data can be commercialized. The hosting is one part, services on top, many different things. You should also get attention and attribution. And then we focus on less work by innovation. So you do reusability, deduplication of effort. There's AI assistance with human in the loop to check the suggestions. Then there should be off-the-shelf applications. So this is data with software. You want this data set loaded with this database on this server. Yeah? And then power tools for curation. So here's a little strategy overview. Right now, well, DBpedia is the most successful open knowledge graph since, okay, here's 2008, it's 2007 actually. And now we're taking this to a global level with this global DBpedia platform, which fosters communication, collaboration, enables sharing of efforts and results, and maximizes societal value. And the medium-term goals is that people can share their value via, organizations can share their values via the platform, effective contributions by third parties, and also that there are thousands of new open data businesses and initiatives to evolve around the platform. So I showed that we bootstrapped the linked open data cloud, and actually, if you want to know what is the largest knowledge graph on Earth, it's not residing in Google. It's actually on the web, stored decentralized, because linked open data is the largest knowledge graph. This is just an image of it. I'm sure it's much larger because we don't know of more, but this is it. It scales a bit like the web. Now, it works. There's great value there, great open knowledge graph on the web, but there are some problems with decentralization, which doesn't make it so effective as it could be. So this is kind of like what we mean with lot custody. We want to coordinate decentralization to give value back to individual nodes. So the idea is you have data, you publish it via linked data, then our platform helps you to become structured and interlinked and synced with other data sets. So I'm going to show the digital 10 actually, because we started 10 late, huh? Okay, I good. So I'm going to show you one of the interfaces. So this is this website here, the Data Bus, is an online platform, and it's completely created out of posted metadata from files from users. So you can see recent activity. There's already still in beta, but there's over 0.5 terabyte of data on the bus already. And we have individual accounts like on GitHub. Jumps back. So what is it? It's actually a registry of files on the web, so virtual file warehouse, decentralized file storage. Each database user stores their own data and then just publishes the metadata. And the good thing is here, the data is completely downloadable, so if you had a warehouse, you would know where exactly each box is, and you could retrieve it to build more things. That's why it's called Digital Factory Platform. It has very very loose rules for files, but very strict rules for metadata. So it keeps provenance, clear provenance of the account. Machine readable licenses. You have to assign all the data with your private key, so there's a clear sense of trust that this user has published this data on the web. You have dataset identity and you have versioning. So it's a minimal core, but everybody can add systematically more metadata. And the model works like this, that if you have these boxes, each of the stacks represents a dataset identity, and then each box represents a new version of the same dataset. And this is something, so it's abstract identity and then the individual versions. And in the boxes are several files. So this is kind of like a new model, but it solves many things, because then you can get an update on this and this data set, you can get a specific version of a data set. And here is a property which I'm especially proud of. So it's a data repository where you can systematically query and download all the data on it. This is normally not given, so you have a lot of talk about data repositories, but then you cannot download anything. But here you do a query, you query for the download URLs, you can systematically download the whole bus at once. So it's complete open data, open access, very stable to build applications on it as well because of this stack model. And we also provide user-created collections, so you could bundle your own data sets together to predefine some sort of application for certain applications. There is a download client which helps you convert existing data, so you have a download as function, you can download bzip2 compression as gzip. It does file format conversion, and it also can include mappings like CSV to RDF. So you can transform the data on download. You can build relatively complex pipelines, won't go into details so much, but this is the new DBpedia release workflow. So it's published twice and evaluated twice. So there are different kinds of tests you can run at each different phase after publication to the bus. And you can take these tests and directly improve the software. So this is aligning data and software. Another thing we will build, or we already started building, is the DBpedia Knowledge Library, which has the mission to improve external data. So kind of like caches the core fraction of digital data, so-called master records, and indexes them. It has a curative focus, so it contains ontology, mappings, and links. And it also has AI assistance, yeah, to guide the effective curation. Yeah, okay. I'll skip that. So now, okay, these are some of the last slides. We implement something called FlexiFusion, which has several use cases. There's a pre-fusion, which is an aggregation of all data. This is what you have seen in the initial interface, where you could compare the values. There's a fusion. This means there's an algorithm that decides which one is the best value, but this is always a bit critical. FlexiFusion provides source enrichment, so you can get additional data for your data, or you do export. Yeah, what is the fusion? There's a demo of the fusion result, which I will not show you, or I'll skip it for now. But so we aggregated all the data sets you have seen the logos before. And this results in a huge consistent knowledge graph. They have 3.8 million birth dates, for example, collected from different libraries into a unified data set. So this is what you can download, and this will grow relatively large because we are scalable global ID management, and it will allow to create the second largest knowledge graph out of the largest open knowledge graph. So we take lot and we build a smaller knowledge graph. Okay, so maybe the next steps. So we are hiring, so we're looking for 2 female or other PhD students to help us build this AI assistance. And we are also looking for strong partners to help us set up national data infrastructures that sync with the global DBpedia infrastructures. So because it's a super node platform architecture which can be hosted on national level or local level or domain level. I'm finished now. Thank you.
Thank you, Dr. Hellmann. As we are running out of time, just I think fast a couple of quick questions.
I cannot hear you. What was
No, he says why there is gender bias in what context? I don't know. We're looking for two female and the other page build AI. Yes. Okay. Yeah. I don't know. Did you get his question?
No, I didn't.
No. We are looking for two female or other PhD students. Our other is there. Okay. PhD students.
Totally PC.
Yeah, one more question, of course.
Yes.
Technically, that's not a question.
Good afternoon, everyone. I'm Naresh Kumar from Central University of Haryana. My question is, you talked about the online ontologies, which is maintaining automatically. So I'm thinking that it is maintained by crowdsourcing, or how it happens?
Yes, at the moment it's maintained by crowdsourcing. There's 300 editors which edit the ontology, right? So they created it. It's very rich. I think it has over 2,500 properties and thousands of classes. But adding more people to this editing process, it does not work at the moment, because then if you make changes now, applications will break. Yeah. So you can have destructive edits actually, the maintaining it is very hard. So things change, and then you need to update it. And everybody likes to create stuff, but then updating is not so so we are switching here into a more flexible approach. So in the future, this is also part of the knowledge library. So we are clustering the properties of all ontologies in the future, and we're creating property clusters. So in the future, it will not matter really what vocabulary you use, because our knowledge library can translate it. So you can download one data set, which is in schema.org, and you can decide to download it as Wikidata properties, for example, or any way you want it, or FOV, and it does the automatic syntactical conversion of the properties. So that is what we're aiming for.
All right, thank you.
Oh, thank you, Dr. Hellmann, for a wonderful lecture. I know that crowdsourcing has its own challenges, because data cleaning becomes even more a rigorous activity, I guess. Okay. Thank you very much for an enlightening lecture on DBpedia.